Welcome, everyone, and thanks for joining our talk. Today, we are going to talk about context-aware segments, which is a way of reorganizing segments based on context. Short introductions. I'm Tejas, work in Amazon, have been working with OpenSearch for the last 3 years and have been focused on mostly vector search.
Hey, my name is Rishav. I have been in Amazon for about 7 years, in OpenSearch for about 4 years, where I mostly work on indexing. I am an active contributor and a maintainer in OpenSearch as well.
Cool. Um, Before I dive into the concept of context-aware segments, I just want to give a quick primer on how OpenSearch arranges the data. So an OpenSearch index will basically partition the data into shards, and each shard has segments, multiple segments. Segments are where your data lives, and it basically uses classic scatter gather. Basically, it'll just fan out your query into all the shards and eventually execute it on each and every segment and collect all the results. Now, this pattern works well for most of the cases, but there are a few cases where this pattern just leaves the gains on the table, like mostly performance gains. Um, Diving a little bit more into segments, like if you're familiar with LSM trees, it's analogous to SS tables, basically immutable sorted data files living on the disk. Uh, so in OpenSearch, like these are basically Lucene segments, and these are sorted by doc IDs, and any underlying data structure like postings or stored fields are just leverage this sorted doc IDs. Um, Now, internally in Lucene, there is a concept of document writer per thread, which is basically DWPTs, which is analogous to mem tables. Um, you can think of it as like it's a buffer of when you're writing an index, it's basically a buffer. And this buffer is then flushed into the disk, and those become segments. Now, these DWPTs are pretty a really good way of enabling concurrency. This enables concurrency without any sort of contention during writing. So the idea is any DWPT, any thread that is free while writing, it'll just pick it up and then write the data in it, and then it will eventually get flushed. Uh, the drawback of this approach is that it doesn't consider what data it's putting in where. So it's just random distribution based on the availability of the thread inside the shard. Uh, so it has absolutely no context. It's basically context blind in terms of data. And as a result, it is context blind in terms of queries as well. So that's where the drawback of this scatter gather is. Now, before diving into context-aware segments, let's understand a couple of use cases just to highlight the problem here. Now, here I'm taking an example of like a very common HTTP log analytics use case. In most of these workloads, you will have your success 200 codes more, relatively more, compared to your error logs, mostly in the production environment. Even though your data is like mostly about success logs, your query patterns will be around error logs. Now, in this example, like I've given 5 segments, and each red dot is basically an error data point where your query will search. Now, in a classic OpenSearch way, when it does scatter gather, it will just go through all the segments irrespective of what the query is. And because the data during indexing, the arrangement of the data is just completely random. So now each gray dot is basically representing a wasted CPU, a wasted disk IO, which absolutely doesn't contribute to your search results. It'll scan all the documents irrespective of what you want. Um, Now, how much waste are we talking about here? We just ran some numbers, and then what we found was like across different queries, we were seeing different numbers. So, in a typical range query for log analytics, we found that it's going through 3 times more documents. And in a sort query, it'll go through 15 times more documents. And aggregations were the worst hit, where it goes through 40 times more documents than it's required. Apart from these added computes, what we figured out was even compression gets affected with this like random ordering. As soon as the as soon as we order the data correctly, we found that the compression also works better, and we saw almost 20% gains in compression. And what we have seen in general is smaller your data, the better performance you will get in general. Uh, so yeah, there is no data change, no algorithm change, and we still see better results with better ordering because compression is better. Um, I also want to dive into another use case just to highlight the problem in a different way. So in vector searches, like vector search in general is a very memory hungry scenario. So in vector search, like we create HNSW graphs. It's an approximate nearest neighbor search, and the idea is like we just navigate a certain portion of the graph to be able to navigate, to be able to get like the closest similar neighbors. Uh, Now, like take an example where there is, let's say, an organization which has a single index, and that index basically has embeddings for various other teams. Now, most of the times, the query patterns are in a way where uh, a particular team will only filter out their data and then search for these embeddings for the nearest neighbors, basically. But when we when OpenSearch indexes the data, it basically creates a graph of various teams in a the data inside the graph is for multiple teams. Now this works fine most of the times because as long as your data is not skewed. For example, if we have equal amount of data in different tenants, then it just works fine. But like if there is skewed data, and in most scenarios there is, this falls apart a little bit. Now, one thing, so these graphs, each of these segments need to be loaded inside, need to be there in the memory to be able to do a graph search. So let's say there's a tenant which has just like 10 documents, and there is another tenant which has 1,000 documents. We still have to load those 1,000 documents just to find those 10 documents. Uh, so there is like a performance penalty there, as well as you are eating up more memory, or you are just slowing down your searches if you don't have enough memory. Um, Apart from just the memory constraint and the low performance, there is also a degraded recall here. So the quality of the search results for the tenant which had just 10 documents goes down significantly. The reason being, uh, when the graph search happens, it only explores till a exit condition is met, and if it doesn't go and do and go through all the nodes, even if it doesn't find any data. Um, so in that scenario, like there is a good chance that even though the segment has the data for the tenant, it just didn't reach based on the entry point of the graph. So for big tenants, we see like the recall doesn't drop at all, but for smaller tenants, the search quality degrades drastically. So yeah, this too, I hope, highlighted the problem of scatter gather. What when there are for these two use cases at least. Um, let's dive into context aware segments now. Like I'll let Rishav handle the initial part of it.
So thanks, Tejas, for setting up the context. Yeah, basically, as we discussed about different cost due to scatter read, which is currently happening in OpenSearch, and basically it leads to it's end up burning like CPU. It ends up bloating memory, as well as it defeats the compression. It also impact compression algorithms as well. As we saw, like there is some impact even in the compression as well. So all of this is because like related documents are spread apart. So question here is like, what if document assignment within a segment wasn't purely concurrency based? What if we considered actual anticipated query patterns as well while assigning documents to within a segment? So if we, the reason why we are thinking in this fashion is because if we think about it, we know how user usually query a pattern for a particular kind of workload. So basically, for log analytics, filter is usually on the basis of the error code. For multi-tenant use case scenario, like it is usually on the basis of a particular tenant ID. Similarly, for time series dashboard, like it's usually on the basis of a time range. So these access patterns are something which are predictable, and they are defining a natural groups of how the related documents are actually. So even then, like basically data distribution that is currently happening within a segment is actually completely blind to these patterns. It is only driven by DWPT threads. It's only driven by like which DWPT threads is basically happens to be free at a particular point of time when ingestion is happening. And this leads to related data being scattered across each and every segment. And so question here is like, what if we align segment boundaries with these anticipated query patterns that we saw for different types of workload? And like, what if like engine co-located related data so that query targeting one group only needs to read the segment that holds it? And this is what we are exactly building in context aware segment. And basically yeah, like I think we can probably start looking into how data is organized with context aware segment. So as we can see, like here in this particular diagram, context aware segment aligned boundaries via anticipated query pattern. So this is the same data like that we saw in one of the previous slide, and it's like the same document, but now the data is being organized via context. So error logs, which are like 4xx and 5xx logs, are living in their own segment, which is segment 1 here, and the success logs are which are like 2xx and other logs, which are like queries which are queried like less frequently, are in like segment 2 and segment 3. So this layout actually reflects the access pattern in which query will access these data. So like in case like now, if user tries to query a particular document, like say if they want show me what all 5xx errors are, it can immediately scan skip segment 1 using the context, and it can skip rest of the document, ensuring that there is no wasted read. So a common analogy of this can be basically reorganizing books in a library. So once we know that a particular once we know that we have sort of like organized the book by section, say a book is like in history section, some is in like technical like some is like programming section. Once we know that a book is in section in a particular section, finding a history book is trivial, and like we don't need to search it, like we only navigate here. So the next question that basically comes into our mind is like, who decide which documents should belong together, and like what exactly related means in terms of data here, and like how we are basically determining which all data documents should be grouped together and which should be kept segregated. The way we are doing there in context aware segment is by something called grouping criteria. So basically, grouping criteria is basically a user-defined function which we are providing during index creation, and it is basically a simple predicate which gets evaluated every time we are ingesting a particular document. And basically, for example, like for HTTP logs use case that we have been discussing so far, the grouping criteria here can be to group the document by the status code category. Uh, like in that case, all the 200 level responses will be grouped together, and like all 5xx logs like will be grouped to another group. Similarly, for multi-tenant use case, grouping criteria can be a tenant ID, ensuring that like those document belonging to different tenant goes to different groups actually. And grouping criteria function that we initially talked about, it is defined. It is something which is defined only once during index creation, and it is a lightweight, deterministic and lightweight. And as discussed, like it is evaluated during the ingestion time. So basically, the overall overhead which we get for evaluating the grouping criteria, that is almost negligible. And there is another dimension to the grouping criteria, that apart from ingestion time, this is also evaluated during the search time to basically figure out which segment should be targeted for this particular query. So initially, the query is something which is remaining exactly the same, but how what is changing is like basically how the optimization happens for executing the query. I think we will talk about like each part on like how grouping criteria is evaluated during the ingestion time and during the query time in separate slides. This is a high-level overview of how context-aware segment is initially grouped. Um, Now that we have talked about what, let me show you how. Like initially, the overall architecture inside the OpenSearch engine that basically takes care of grouping the document, related document together without destroying the overall indexing performance. So before we deep dive, I think I want to talk about couple of OpenSearch terminology that we will use throughout the rest of this particular presentation. The first one is the index writer, which is basically an in-memory write buffer, and basically it accumulates any incoming document and periodically flushes them into the immutable on-disk file called segments, which is similar to, as we discussed, similar segments are like something which is similar to SS table in LSM tree-based system. And second terminology that we will use periodically here is like the internal engine, which is OpenSearch storage engine layer, and it orchestrates all shard level operation, be it indexing, flushing, refresh, or recovery. And basically, one more point to note here is that like uh, currently, like internal engine basically delegates all write operation to a single index writer. I think we will talk about it, like what are the consequences of this and how like context aware solve these issues at later point of time. And third is like refresh. That is the operation that OpenSearch periodically performs to make recently indexed document visible to the search for query time actually. So basically, unless a refresh get trigger, newly indexed document only exists in the in-memory buffer and not yet available for the search. So these are the building blocks that we are going to use from here on. And with this terminology in place, let's start looking into the architecture of the context-aware segment. So as we are discussing, like today, each shard in OpenSearch has exactly one index writer, and this writer essentially accepts document, buffer them into the memory, and flushes them into the segment on the disk in the form of segment, which is basically analogous to SS table. And search query then read data from these segments, and the entire architecture of indexing search replication is something which is based around this assumption that one writer will be present for each engine or one shard actually. To achieve like context aware grouping, what we are doing is basically we are maintaining a separate writer for each group, ensuring that whatever segments that are getting generated from each of the writer, like belonging to a specific group, belonging to different groups, remain segregated. However, uh, since we discussed, the current architecture does not allow like multiple writer per shard. It's only a single writer, and all the downstream operation like basically search, replication, and checkpointing that we initially discussed like depends on it actually. So in order to like ensure that the contract of one writer per shard is actually not broken, we introduce something called a composite index writer, which is basically a component that internally manage a pool of group specific writer, but externally it is presenting itself as a single view to the internal engine actually. So basically, like talking about the log analytics use case that we basically discussed right now, like uh, Composite index writer will basically maintain a pool of group specific writer, one for 2xx document, another for 4xx, and one for 5xx. And each group specific writer independently buffers and flushes document into its own segments. And all write operations that we will performing will be routed to these group specific writer during the ingestion time actually. um, the second part where we are basically during which is the refresh time, where we basically make ingested document visible for the query. Composite index writer, which is the common layer of the group specific writer, will periodically sync the segment produced by each group specific writer, making newly indexed document visible to the search. uh, and it will also ensure that during this time the group specific boundaries are remaining intact within each segment. So this is like a high level architecture. I think we will dive deep each one of them one by one in the next slide. Um, let's start with the indexing part on uh, how context aware segment part is initially handled during the ingestion time. So we will start with a example where we are indexing a batch of HTTP logs with different methods and like different status code. I think first one is like get with a 200. Second is a post log, which we are ingesting with 403. Similarly, there are some 5xx logs as well. Um, the grouping criteria that we have defined, the grouping criteria function that we have defined for this index is evaluate documents by their status code. So a 200 and 201 status code logs will be evaluated to grouping criteria 2xx. Similarly, like 403 resolved to 4xx, and 503 and 500 will be resolving to 5xx. As we can see in the like diagram as well, that basically document gets routed to specific group specific writer. So 2xx document got went to like 2xx writer during the ingestion time. Based on the grouping criteria that we evaluated, like it got routed to the specific group specific writer. 2xx went to 2xx logs went to 2xx writer, 4xx logs went to 4xx. Similarly, 5xx 503 to 5xx writer. And these three writers are three independent path. Basically what I meant is like in case like basically if there is any ingestion performed for 5xx writer and there is a lock on 5xx writer, like during that particular time, like 2xx writer can independently accept request, ensuring that there is a full parallelism across different groups. And like there is one more thing, like in case like say if a particular document is like getting ingested, group for a document belonging to a particular group is initially ingested for the first time, we will be like basically instantiating a writer corresponding to that particular group for the during the ingestion time on demand actually. um, so let me slow down here a bit more and like basically zoom into exactly what is happened when we are ingesting a particular log. So for 503, like say like I think we are zooming into here like where we are indexing a 503 document. As we can see that like the grouping criteria initially evaluated the group here for 503 as 5xx, and like the engine basically post that like during ingestion time the engine looks up the writer pool, which is basically a concurrent hash map and keyed by the group level. And basically here like the engine finds the writer corresponding to find the 5xx corresponding writer. And in case like it is if it is unable to find any writer in the pool for this particular group, we that means like we are ingesting the document for this particular group for the first time. It creates a new writer, ingests the document into it, and then puts it back to the writer pool. So yeah, like I think as I discussed, like here like post it figured out like what is the writer. It performed the ingestion over it, and then it puts it back once the ingestion complete. The write lock is released, and it puts the writer back into the pool. And this is how like we ensure that during the ingestion time, uh, like uh, like context aware segment is basically enabled. Um, Moving on to the next part, which is basically the refresh, and which basically makes this ingested document visible during the search time. So like basically as discussed, uh, like uh, basically uh, refresh is basically enabling the ingested document visible for search, and it's actually the bridge between indexing and the search, and it's basically the moment where buffered document becomes visible, and like searcher can basically searcher can basically use it to query like the ingested document. um, but like there is one issue here, that with context aware segment we have to also uh, make this bridge work without blocking either side of things actually. So basically ingestion and refresh should continue to work. Ingestion and refresh should be continue to work parallelly. To to solve that, we basically use something called double buffer pattern that is inspired by a graphics programming. So as you can see, like composite index writer here maintain two slots for the writer map, which is basically a current slot and an old slot. Current slot is where like which is basically holding the active writers, and it is taking the active ingestion for 2xx 4xx and 5xx logs, while the old writer is something which is empty. When refresh triggers, like what we are doing is like we are rotating the writer map here, where the current writer is atomically moved to the old slot, and a brand new empty map takes the current slot. um, and this rotation is something which happens under a write log, uh, but since this is just a pointer swap, it's not like too big of an operation. It completes like within few nanoseconds. And basically once rotation completes, incoming document immediately creates fresh pool of writers uh, in the current map, while the old writer is something which is frozen, and old writer is something which is not accepting any new writes, and all active writes will something which will be going to the current map. This ensures that new indexing does not wait for refresh, and refresh does not blocks new indexing, thus ensuring the uh, uh, two operation completely works on independent timelines. um, as we can see, like at this point, like I think like the old map is something which is frozen, and the new map is something which is accepting the new set of right. Next step is that we want to look here is like how we need to sync the document sync these document to the parent writer, so that searchers can see them actually. So uh, yeah, like as we can see here, like the next with the map being rotated, old writer are frozen, and it is ready to be drained into the parent writer. And basically the way we do that here is like each writer in the map, uh, in the old map, is basically uh, processed sequentially. Like first, like all the writers in the old map is closed, which flushes all the in-memory buffer or in-memory buffer document to disk as a segment file. Uh, then the parent index writer, we use something called add indexes API, which is like a Lucene internal construct, which is used for syncing all the documents of the child writer with a parent index writer, which basically copies the segments into the parent directory and registers it, so that it becomes available for search. And finally what we do is like we also delete child writer directory as well, so that post that, like only child writer is something which is not existing. It's only a single writer, which is the parent writer, and each having and within parent writer there are a bunch of newly created segment, and each one of them is essentially tagged with its own group specific attribute. um, yeah, so once all writer have been synced, like as we can see here, that the parent writer, the newly created segment that we have created, the parent writer is something which will be holding this, and each of these segment will essentially contain document only from a single group. And like post this, like the searcher then opens a new directory reader on the parent reader, and sees everything through a unified view, while individual segment remain internally coherent. So till now, at this point of time, we talked about ingestion, we talked about how ingested document becomes visible for search via a refresh function call, which are actually the happy paths as well. Um, Now let's look into like another problem statement called updates. Because like in real world system, like it's not only a document can be updated as well, not a single only append doesn't happen here. So basically this is actually introducing a new version consistency challenge across writer, which is what we will look into next. So yeah, like as discussed, in a general, in a log analytics use case as well, like there are scenarios when a document can be updated by the customer, or there is a possibility that uh, a document can get updated even via coordinator retries. So uh, in that case, like what will happen when a document that already exists receive an update with context on a context aware enable index. So to take to explain that, like we are taking an example again. So say like a document, let's call it doc 42, was indexed in the previous refresh cycle. It passed through the grouping criteria function. It landed and basically say like it landed in the group that get evaluated for that particular document is 5xx, and it landed in 5xx writer, was synced to the parent index writer during refresh, and post that it becomes available for search. Now say a new version of the same document, doc 42, arrives, and with the same document ID and an updated content. Um, in this particular case as well, the grouping criteria function will fire again. The grouping criteria function will again have evaluate the groups to a 5xx for this particular document as 5xx, and it will be routed to a 5xx writer. But the case here is that the new version that will land in the current cycle, it will land on the current cycle 5xx writer, not on the old writer where the actual first version of the document is existing. So basically, this can lead to a scenario when, like, when say like refresh gets triggered at this particular point of time, what can happen is both the new version and the old version of the document can basically exist on the parent writer, and this can lead to a correctness violation actually. Earlier, since both of them were landing on the same writer, this issue was not there. But now, since document for the different document for the same document for with different version can land on separate writer, this kind of correctness violation can happen. So question is like, how do we solve this? Let's look into the solution as well. So solution here that we are using is like it's a two-phase approach. So at the right time, rather than immediately deleting the old version from the composite writer, what we are doing is like we are maintaining a separate uh, buffer called a delete entry, which contains the document ID, version, sequence number, and like primary term. These are like some internal metadata information. So basically, what it is doing is like it records the intent to remove the old version from the parent writer without acting on it immediately. And basically, there is another component. There is another part to this particular solution, that during the refresh time, like basically before syncing the new segment from the child writer, composite index writer will also drain this new buffer for delete entry, where basically for each entry it will apply the soft delete to the old version and then sync the new version from the group writer, so that post refresh exactly one version of the document is visible. uh, let's look into each of this step in detail. So as you can see, like apart from like ingesting the document, like composite index writer also did one more thing, to maintain a bookkeeping entry for each update operation. And this entry actually recorded the delete intent for the old version, and it also signifies like which particular document, uh, ne- previous version of which particular document needs to be removed for the from the parent writer at the next refresh. Second part is like version settlement. where like which happens during the refresh time. And basically, what composite index writer does here is like it drains the buffer delete entries that has came so far, and for each delete entry, it will basically perform a soft delete on the of the older version on the parent writer, making it invisible. And basically, then it syncs the new version of the segment from the group writer, thus ensuring that after refresh, only a single version of the document is something which is visible. Um, so till now, like we have talked about like how ingestion happens, like how we makes it available to the refresh, and how we are taking care of like version synchronization, and we are keeping it consistent. Um, there is an another scenario that we need to handle with context aware segment, and like this is something which we need to handle it during compaction. So as like I think most of you may be aware about, like LSM based system periodically merges smaller segment or smaller SS table into larger ones, so that system remains healthy, and basically it also avoids like unbounded number of segment files, and like file handles doesn't breach limit. But with context aware segment, we discussed, like we are introducing a new invariant where every segment belongs to exactly one group. So this invariant can cause an issue that basically we cannot allow a 4xx segment to be merged with a 2xx segment, as this would destroy the grouping guarantee that the entire system of context aware segment depends on. Therefore, like in order to solve that, uh, in order to enforce that we have like this strict constraint, we are creating our own new merge policy, which is ensuring that segment for the same group are eligible to be merged together, but segment from different group are never considered as a merge candidate uh, in any case. And apart from that, like we are also introducing a custom codec that stamps the group specific attribute both at the segment creation time as well as during the segment merges, so that like when two 4xx segment are merged into one, the resulting segment inherits the 4xx label altogether. um, I think parallel to this, like there is even a case of force merge scenario as well, like where basically we are actually enforcing the force merge as well on per group level now instead of per shard level. I think with this, like we covered like indexing and search and refresh as well as merge. I think I will give it to the mic to Tejas now to basically explain how context aware segment is handled during the merge time. Oh, sorry, during the search time. Yeah.
So yeah, let's look into a bit into how search works here. Now, all this indexing work that we put in grouping segments will only help if search is able to leverage it. Uh, Current scenario is like OpenSearch will just go through each and every segment and just execute search on it. Now, with it needs to be able to leverage this grouping information to be able to prune the segment space, to narrow down the search space, basically. Uh, so yeah, the very first step of it is like to figuring out the group from the query context itself. Like for this, what we did was like we are leveraging the existing Boolean query clause, Boolean query itself, and then there are multiple clauses in which we can exactly determine what the query context is and what the grouping is. For instance, like filter is a strongest signal for us. Like as soon as we get a grouping inside of a filter, we can just stop traversing the entire query tree and just go through and figure out the grouping from there. Similarly, must is like an and clause. So as soon as we find that hey, grouping is 500 or 400, like we from the must clauses, like we can just ignore the should clause. And if out of these clauses we don't find it, we just execute search on all of the segments. So it just goes back to the fallback of traditional going through each and every segment. Now, the pruning part is where exactly the benefits of performance lie for context-aware segments. So instead of going through and filtering for each and every query, which is a naive approach, what we did here was we are leveraging the refresh mechanism here. So while refreshing, we have the view of all the segments, and we create a map of segments to group to segments, which helps us do a zero cost filtering here. So yeah, this is an end-to-end flow. The only two added steps here are group extraction and segment selection, which is pretty lightweight. Some benchmark queries results here, which we see around 30 to 40% improvements. And yeah. Yeah, thanks a lot. And these are some QR codes if you want to read up more on it. We can, yeah, thanks a lot.